So here's how we find or we approximate the instantaneous rate of change from an equation, and we do this with something called the difference quotient. So let's look at an example. This green graph here, I'm just going to take out my ruler. Let's say we wanted to find the slope of the tangent at 1, where x equals 1. So basically, just to sketch that in, we want to find the slope or approximate the slope of that tangent, right? Let me hide that ruler. So the way we do that, is by using the difference quotient. And just like we did in the previous question, by the way, you should have watched the previous video on secants, tangents, and difference quotient. It gives you some sense of what this is, right? And essentially what we're going to do is we're going to approximate the tangent. We're going to approximate the slope of the tangent by, if we're looking for this point right here, we could, for example, find the secant between 1 and 3, right? So the slope of the secant there, that's a decent approximation of that tangent line, right? We could go even closer. We could do the secant between 1 and 2, right? See how that's even closer to the slope of the tangent? But if we wanted to approximate the tangent even more, we can zoom in on that point. And let's say we wanted to find the slope of the tangent between 1 and like 1.01. So we wanted to find the slope of that little tiny line there. And that's going to be very close to the slope of that tangent line. And essentially that's what we do. We find that difference. And we call that difference, actually, that difference between 1 and 1.01, whatever that is, we call that h. And in this case, I've used h as 1.01. Sorry, no, not 1.01. There's my eraser. Just 0.01, because that's the 0.01. That's the difference between those two values. We could, if we want to be a little bit more accurate, we could make that 0.001 or even 0.00000001. Basically, it comes down to how much time do you got and how accurate your calculator can be in order to calculate that. But the smaller the number is, the more accurate this is going to be an approximation of that slope. So the equation we use to do this, it's basically the same thing as before, as finding the average rate of change between 2 points. So it's still delta y over delta x, the change in y over change in x. And the change in x, that's the easy part, right? Because that's just how much the x value has changed between those 2 points, which we're just calling h. The y difference is what the function is at x plus h. So in this case, x plus h would have been that 1.01, right? So what's the function equal to at 1.01? And then we're going to subtract what the function is at 1. So essentially it's the same equation, and that's what we use for the difference quotient. So let's see what this looks like in practice. Let's do an actual problem. Okay, so we're asked in example 3 to approximate the instantaneous rate of change for that function at x equals 2. So our first step is to apply the difference quotient. Whenever we want to find the instantaneous rate of change, we can apply the difference quotient. So I'm just going to write out the formula for the difference quotient. I'm going to put IRC, instantaneous rate of change, is approximately equal to f at x plus h minus f at x all over h. Okay, now I plug in my function. So my function there was 0.5x squared minus 1. Now, if we want to evaluate the function at x plus h, that's going to be, 0.5. And instead of x, it's going to be x plus h, right? Squared, minus 1. And then the function at f of x is just going to be the function. So 0.5 x squared minus 1. And we put this all over h. I'm going to as h. Okay, so now, in order to find or approximate this instantaneous rate of change, let's just plug in what we know. We have our expression. We can just plug it in. So we know we're going to plug in our x value as 2 because that's the location that we want to find the instantaneous rate of change, right? So I'm just going to put this off to the side. X equals 2, and our h, let's make it 0.001. Just a small value, and let's see what happens when we plug those things in. So 0.5 2 plus 0.001 squared minus 1 minus 0.5, 2 squared minus 1, all over 0.001. Okay? When we do that in our calculator, we get 2.0005. So usually we don't carry that many decimal places. Let's round to 3 decimal places, or 2 decimal places, which rounds to approximately 2. Remember, this is approximate. So it comes out to 2, essentially. If we look at our answer, the exact answer here is 2. So if we were to use some calculus to find the exact answer, that's what calculus does, we would get that it's 2. We came out very, very close with 2.0005. So you see, you don't need to plug in an h value that's that small. 0.001 will mostly work unless you're already dealing with very, very small numbers, in which case you should use an even smaller number for h. So that's the process. Let's apply it to a few more questions. Okay, here's another question. So it asks us to find the instantaneous rate of change at 3x squared minus 4x plus 8 at x equals 2. I'm going to change up this question by adding a part. So we're going to find the rate of change at x equals 2 and x equals 3. So we're just going to make it a little bit more long, basically. So let's start off with our instantaneous rate of change. So the difference quotient says it's going to be f at x plus h minus f at x all over h. And we just plug in our formula there. Every x we're going to replace with x plus h. So 3x plus h squared minus 4x plus h plus 8. And then subtract the regular function, just f at x. 3x squared minus 4x plus 8. All over h. Okay, so last time we just plugged in the values we know. But this time we have to plug in 2 separate values, 2 and 3, right? We need to know what both of those rates of change are. So before just plugging them in, it might be a little bit easier to just simplify that expression first. Okay, so let's try that. Let's try to simplify this whole expression to make it easier for us down the road. So that's going to be 3. I'm going to simplify this, x squared plus 2xh plus h squared minus 4x minus 4h plus 8 minus 3x squared, barely fits, plus 4x minus 8. Whoa, that looks crazy. But look what happens. Already, this 4x and this negative 4x and that 4x are going to cancel out. This 8 and this negative 8 are going to cancel out. So it's already gotten a lot simpler just by canceling a few little things out. And this actually happens a lot when we deal with these things. Okay, so let's continue. Continue simplifying. 3x squared plus 6xh plus 3h squared minus 4x minus 3x squared all over h. Oh, again, this and this will cancel each other out. That makes it a little bit easier. Oh, I made a mistake. Did you see where it is? This should actually be 4h here. So this should actually be 4h. Sorry about that. So let's simplify. Simplify even more. So 6xh plus 3h squared minus 4h all over h. What do you notice about the numerator? All the terms have h in it, so we can actually factor out an h. That's the only thing we can factor it, I think. 6x minus 3h minus 4 all over h. And then we see that those h's cancel out. So the final simplified version of this, of the difference quotient, is 6x minus 3h minus 4. That's much simpler than this thing up here, right? Notice how those two things are equivalent to each other. Just one is a lot simpler. So when we need to find the instantaneous rate of change, remember this represents the instantaneous rate of change, or it approximates the instantaneous rate of change. So if we want to find the slope of that function, the instantaneous rate of change at 2 and 3, it's much easier to use this, to plug in 2 and 3 into this, as opposed to plugging them both into that original function. So often I'm going to have you simplify the difference quotient before plugging in values. So in order to do it, let's do it at 2, at x equals 2. The instantaneous rate of change, we'll use h equals 0.001 again. So let's do that. This is going to be IRC is approximately equal to 6 times 2 minus 3 times 0.001 minus 4. That gives us 7.997. Okay, and if we round that to 2 decimal places, that's going to be approximately 8.00, essentially. Okay, not bad. And at x equals 3, we'll use h as 0.001 again. We have IRC is equal to 6 times 3 minus 3 times 0.001 minus 4. It's a little bit messy there. But what we get is 13.997. Okay, which is approximately equal to 14. They won't always come out to nice numbers like this. It just so happens, I'll make it 14.00. It just so happens in this question that it does. Okay, so there we go. We found two different difference quotients, two different instantaneous rates of change of a function by simplifying the difference quotient. So the next question asks us, going back to example 4, determine the equation of the tangent line at x equals 2. So let's think about what we've found so far. First of all, we know we have a quadratic here. So that function that we're given in the previous question is a quadratic. So it'll look something like that. I don't know exactly what it looks like. I'm just drawing it. It opens up and whatever. Doesn't matter. We want to know what the equation of this tangent line is at x equals 2. So say that this is 2 here. Our tangent line at this point is going to look something like that, right? It's going to just touch at that one point. So we want to know the equation of that line for this question. What's the equation of a line? Y equals mx plus b, right? So that would be the equation of that line. What do we know about that line, though? What have we found so far? Think about what we found in the previous question. We found something at x equals 2. What did we find? Remember, we found the instantaneous rate of change at x equals 2. And we found out that that was equal to 8, right? Remember what the instantaneous rate of change is. The instantaneous rate of change is just the slope of that line, right? That just touches at that point. So we know the m for this is going to be 8. Okay? That's the point of what we did in the previous question. We found the slope of that tangent line. So we know that equation is essentially going to be y equals 8x plus b. We need to find now the other part of that equation, b, which we should know is the y-intercept, right? How do we find the y-intercept? Well, if we know a point on that line, we can just substitute it into that equation. Luckily, we can find a point on that line, right? We know that that is a point on the line where x equals 2. So what is our function at 2? We can just plug that into our original equation, 3x squared minus 4x, so 2 squared minus 4 times 2, what was the third part? Plus 8. So that equals 12. So that tells us this point on the line is going to be 2, 12. Right? Obviously, I didn't draw it to scale because that's a positive value, but it doesn't matter. So 212 is on the line. So basically, in order to find b, we can just plug in 0.212, right? So 12 equals 8 times 2 plus b, and, oops, that should be an equal sign, and that makes b negative 4. So the equation of our line is going to be y equals 8x minus 4. There we go. That's the equation of that tangent line. So we needed the difference quotient to find this part of it, and then the slope, basically, of that line. And then we used just a little bit of algebra to find the y-intercept. So for example 6, I want you to try it yourself. Pause the video here, try it yourself. And one other thing I want you to try to do, I want you to try to simplify the difference quotient instead of just plugging in things at the beginning. This just gives you a little bit of practice with algebra, and you're going to see this algebra coming up, so it's important you practice it. So pause it now, and then unpause it when you've found a solution. Okay, there's the answer. That is a lot of algebra, and I didn't do it the most efficient way. You may be able to do it a little bit more efficiently, but it just has to do with simplifying fractions, canceling some stuff out, and you get your final simplified difference quotient looks like this. Not actually that simple, but when you plug in x as -1 and h as 0.001, I got my instantaneous rate of change at that point is 3.003, or approximately 3. Okay, let's move on to this last problem. This has the trajectory of a toy rocket given by an equation where s at t is the distance above the ground in meters and t is in seconds. So it's asking us basically what the instantaneous velocity of the rocket is at t equals 4. So it wants to know the speed of the rocket at 4 seconds when we are given the equation for the distance. And one thing to keep in mind, this is a physics concept, but it's pretty straightforward. The instantaneous rate of change of a distance graph or a distance function is velocity. Because think of distance as just how distance or velocity as how distance changes per time, right? So if distance is in meters, velocity is going to be meters per second, how that velocity changes per time. So that's essentially all we're finding here. We just want to know the instantaneous rate of change of that function s at t equals 4. So pause it here, give it a shot. Simplify the difference quotients as much as possible before plugging in t and h, okay? Unpause it when you're ready and I'll show you what we got. So after doing the algebra, it should your difference quotient should come out to -10t minus 5h plus 30. And look back at the question. We want to know what the velocity is at a t of 4. So we want to know this at t equals 4. And an h value, why don't we just use 0.001 again? It seems to be working for us so far. And this question is not much different than the previous ones. If we plug that all in, we should get a value of -10.005. Let's think about our units for a second. Remember, the distance graph, or the distance function, was in meters. And what we did is we found how this changes with time, right? So time is measured in seconds, so essentially this is meters per second. It's the change of the displacement per second. If we check back up here, look what the answer was on the page, -10 meters per second. Now, what do you think the negative means there? Think about it. What does the negative mean? Well, to do that, let's think about what positive and negative mean in terms of the question, right? So the trajectory of a rocket, so the path of a rocket basically is modeled by that equation. So the st at t is the distance above the ground. So if the distance above the ground is changing in a negative way, one way to think about it is that it is moving towards the ground, right? It is getting less high by 10 meters every second. So it's basically falling at a rate of 10 meters per second at a time of 4.